The universe is vast, mysterious, and sometimes a little unsettling. Consider the unimaginable force of magnetars, hypermagnetic stars capable of altering entire planets with a single eruption, or the fleeting yet powerful fast radio bursts, FRBs, millisecond-long signals that light up the edge of the universe like cosmic Morse code. Then there are the strange alternatives to black holes, with cores of dark energy that challenge everything we think we know about the nature of collapsed stars. Each phenomenon adds to the paradox of space, concerning yet mesmerizing, and knowing even a little about these extreme cosmic objects makes the universe feel both haunting and humbling. Zombie stars, white dwarfs that defy death. White dwarfs are fascinating celestial objects that exist at the end of a star's life cycle. Commonly perceived as dead, these stars can exhibit surprising behaviors, particularly when they engage in a cosmic dance with neighboring stars. One of the most intriguing phenomena involving white dwarfs is their ability to come back to life through a process known as accretion. When a white dwarf draws material from a companion star, it can reignite nuclear fusion in its core, transforming into what is often referred to as a zombie star. This process not only allows the white dwarf to continue shining brightly, but also leads to complex interactions that challenge our understanding of stellar evolution. The term zombie star paints a vivid picture of white dwarfs that refuse to fade into the cosmic night. Instead of simply dying out, some of these stars engage in a unique process of revival. As they lose their outer layers during their initial life stages, they are left with a dense core primarily composed of carbon and oxygen. However, when they exist in binary systems, where two stars orbit around a common center of mass, they can siphon off material from their companions. This material typically consists of hydrogen and helium, which the white dwarf accumulates over time. When enough mass is drawn in, the conditions become right for nuclear fusion to reignite, giving the star a second chance at life. The process of accretion is not without its risks. A white dwarf can only sustain a limited mass, known as the Chandrasekhar limit, which is approximately 1.4 times the mass of the Sun. When a white dwarf approaches this threshold, it faces the potential for catastrophic collapse. If the star exceeds this limit, it can trigger a Type Ia supernova, an explosion so powerful it can outshine entire galaxies. This event is not only spectacular, but also plays a critical role in our understanding of the universe. Type Ia supernovae are used as standard candles in cosmology to measure astronomical distances, contributing to our understanding of the universe's expansion. Before a white dwarf reaches its breaking point, it may undergo a series of smaller explosions called novae. These events occur when the material accumulated from a companion star ignites on the surface of the white dwarf. As hydrogen from the companion star builds up, it can reach temperatures and pressures sufficient to trigger nuclear fusion, resulting in a sudden release of energy. This outburst can cause the white dwarf to brighten significantly, sometimes temporarily increasing its brightness by thousands of times. After the explosion, the star does not suffer irreversible damage. It remains intact and can continue to draw in material, potentially leading to more novae in the future. Zombie stars typically inhabit what are known as cataclysmic variable systems, where they orbit extremely close to their companion stars. This proximity allows for easy mass transfer, but it also subjects the white dwarf to intense gravitational and tidal forces. As the stars spiral closer, they may even share an atmosphere, leading to further complex interactions. These systems are a playground for astronomers, offering a chance to observe the delicate balance of gravitational forces, the accretion process, and the transformations that take place in extreme environments. Contrary to popular belief, not all white dwarfs die in a spectacular supernova explosion. Some display behavior that resembles a supernova without actually undergoing the final explosive event. These supernova imposters experience irregular outbursts, similar to novae but on a larger scale. Their light may be bright and significant, leading observers to mistakenly classify them as supernovae. However, these stars remain intact, illustrating the diverse fates that white dwarfs can experience. Understanding these imposters helps astronomers refine their models of stellar evolution and improve their classifications of celestial phenomena. The interactions between white dwarfs and their companion stars also lead to the production of X-rays. When material from the companion star spirals onto the white dwarf, it accelerates and heats up due to immense gravitational forces, often reaching temperatures of millions of degrees. This process creates a significant source of X-ray emissions. These X-rays not only provide crucial information about the physical properties of the white dwarf, but also help astronomers investigate the nature of the surrounding environment, including the dynamics of the accretion process and the characteristics of the companion star. While most white dwarfs consist of carbon-oxygen cores, a rare subset features oxygen-neon cores. These stars are unique in their resistance to explosive disintegration, allowing them to survive longer than their carbon-oxygen counterparts. Instead of ending in a catastrophic explosion, oxygen-neon core white dwarfs may experience stable but intense eruptions, extending their lifespans as cosmic predators. Their distinctive characteristics offer a unique perspective on the variety of outcomes that can arise from the stellar life cycle. The material that a white dwarf consumes often forms an accretion disk, a swirling mass of gas and dust that encircles the star. This disk serves as a lifeline, funneling matter directly to the white dwarf while producing breathtaking visual displays. As the material spirals inward, it heats up and emits radiation across various wavelengths, making these systems observable across the electromagnetic spectrum. The study of accretion disks is crucial for understanding the dynamics of mass transfer in binary systems and the processes that drive stellar evolution. Some white dwarfs possess extraordinarily strong magnetic fields that can significantly influence the accretion process. These magnetic fields can channel incoming matter toward the star's magnetic poles, leading to the formation of hotspots that produce concentrated bursts of energy. As the accretion process varies depending on the magnetic field's strength and orientation, these polars exhibit unique patterns of light emission. The study of these magnetic white dwarfs provides insight into the interplay between magnetic fields and stellar evolution, adding complexity to our understanding of these celestial objects. Zombie stars play a vital role in the recycling of materials in the universe. Through their explosive outbursts, such as novae and supernovae, they release elements like carbon, nitrogen, and iron back into space. This process enriches the surrounding interstellar medium, contributing to the formation of new stars and planets. The cycle of creation and destruction embodied by zombie stars highlights the interconnectedness of celestial objects and emphasizes the importance of these stars in the broader cosmic ecosystem. Theoretically, a zombie star could continue to consume mass indefinitely. However, various gravitational and nuclear forces establish limits on how much material a white dwarf can accrete before facing self-destruction. The balance between feeding and the risk of explosive events poses intriguing questions for scientists studying the life cycles of stars. Understanding these limits could lead to new insights into stellar evolution and the intricate dynamics governing the universe. Zombie stars offer a rich tapestry of observational opportunities across multiple wavelengths, from ultraviolet to X-rays. Each spectrum provides unique insights into the star's behavior, temperature, and interactions with its environment. By employing advanced telescopes capable of observing across these wavelengths, astronomers can piece together a comprehensive picture of white dwarfs and their cosmic roles. Through their incredible journeys of rebirth and interaction, zombie stars captivate astronomers and deepen our understanding of the universe. Their unique characteristics and behaviors highlight the complex nature of stellar life cycles. False vacuum decay, a threat that could reshape reality. The theory of false vacuum decay poses an unsettling scenario where our universe could abruptly change as we know it. The concept centers around the idea that the universe may not exist in its ultimate lowest energy state, known as a true vacuum, but instead in a false vacuum, a sort of temporary resting place. A shift to the true vacuum state would result in the laws of physics transforming, the building blocks of matter disintegrating, and the fabric of space itself reshaping. This theoretical process, if it occurs, would upend the reality we know in an instant. A vacuum state isn't simply empty. It contains fields and forces at certain energy levels. Our universe may exist in a false vacuum where the energy state is lower but not at its absolute minimum. Like a ball resting in a shallow valley rather than the deepest one, the universe might be in a state that feels stable but isn't entirely secure. Physicists believe a lower true vacuum state could exist, and a transition to this state would trigger an unimaginable chain of events. Unlike stable states we encounter daily, this false vacuum could be temporary, held together by quantum mechanics, but always at risk of shifting to something more stable. In quantum mechanics, particles can cross barriers in a process known as tunneling. This isn't movement in the usual sense. Particles disappear from one side of a barrier and reappear on the other without crossing the space in between. If a particle within our false vacuum were to quantum tunnel, it could create a bubble of true vacuum. This bubble would be a small pocket where the universe's laws shift to fit the true vacuum's properties, and the energy released would cause it to expand outward at the speed of light. The Higgs field is essential in determining the masses of elementary particles. Physicists speculate that the current state of the Higgs field might actually reflect the false vacuum state, where the Higgs boson holds a stable but temporary energy. If the Higgs field were disturbed enough to lower to a true vacuum, it could initiate false vacuum decay, instantly altering mass, gravity, and even the constants that govern particle interactions. Gravitational waves, ripples in spacetime caused by massive cosmic events, might serve as early indicators of false vacuum decay. If a true vacuum bubble forms and begins expanding, the violent energy release would generate waves powerful enough to warp the universe's structure. Scientists, however, believe that these gravitational waves would be incredibly faint due to the vast cosmic scales, making it a challenge to detect them until it's too late to react. The false vacuum concept dovetails with multiverse theories. If our universe exists in a false vacuum, other universes might be contained within their own bubbles, each with its unique laws of physics. Some theorists propose that these vacuums are part of a cosmic cycle, where vacuum decay might lead to the death of one universe and the birth of another. This shift could mean our universe transitions into a different state altogether, possibly in a configuration where life as we know it wouldn't exist. False vacuum decay may have anything to do with black hole mystery. In theory, the strong gravitational attraction near the event horizon of a black hole may alter the energy landscape sufficient to start decay, therefore producing a real vacuum bubble. Though the likelihood is still under active study, some scientists propose that these areas of strong gravity may be primary sites for starting vacuum decay, governed by rapidly shifting energy states as it expanded and cooled. The Big Bang might have left the universe in a state of false vacuum rather than true vacuum, much like a quick freezing that didn't reach the deepest level of stability. If this were the case, the universe has been in a precarious balance since its inception, and a shift to true vacuum would essentially reboot cosmic laws. The flow of time depends on the laws of physics, and if those laws shift, the structure that underpins our experience of time could dissolve. In this view, the universe as a space-time continuum would cease to exist in its current form, reshaping even how events unfold across what we perceive as past, present, and future. Our universe's structure relies on various quantum fields, each with its own potential energy landscape. These landscapes are like a vast topography of valleys and hills. False vacuums represent false valleys, lower energy states but not the lowest possible one. True vacuum, on the other hand, is the lowest valley, and if the universe finds a way to shift to it, everything governed by our current fields would shift along with it. False vacuum decay would fundamentally rewrite the laws of physics, making structures like atoms, molecules, and eventually life itself incompatible with the new environment. The forces that allow atoms to bond would either vanish or change drastically. As a result, planets, stars, and any form of life would simply cease to be possible, vanishing in the wake of the vacuum shift. The term false vacuum catastrophe refers to the potential that our universe might shift suddenly, a process that could already be overdue on cosmic timescales. Some physicists suggest this decay might take billions of years, while others warn it could happen at any moment, driven by chance or a triggering cosmic event. Between false and true vacuums lies an energy barrier, keeping the universe in its current state. For now, this barrier appears high enough to prevent immediate decay, but any shift that lowers the barrier, like the influence of dark energy or another cosmic factor, could mean the universe would face a destabilizing shift toward true vacuum. Dark energy might be closely tied to our current vacuum state. If dark energy represents a false vacuum, then any major change to this state could either accelerate expansion or halt it entirely, creating a cosmic reshuffling of matter, energy, and space itself. Quantum mechanics insists that a shift to true vacuum is always possible, however remote the probability. Quantum tunneling, the engine behind such changes, remains unpredictable. Despite an extraordinarily low chance of tunneling occurring, the universe operates on timescales and conditions that mean it's always a possibility. The cosmological constant, which shapes the universe's expansion, may be connected to our false vacuum. A fluctuation in this constant could destabilize the vacuum state, pushing the universe toward the true vacuum. If it shifts too much, a vacuum decay could be triggered, essentially rearranging the universe's fundamental structure. Hawking radiation, which is theorized to leak particles from black holes, might play a part in destabilizing a vacuum state. Near a black hole, the radiation could create conditions ripe for vacuum decay, especially in high-energy zones around black holes. It's impossible to calculate exactly, meaning it remains a hypothetical risk that could manifest billions of years from now or sooner. Current models are varied, and many are optimistic that the universe will remain stable indefinitely. False vacuum decay doesn't only concern science, it has philosophical implications too. The prospect that everything might one day end without warning raises questions about existence, time, and the nature of reality. If our universe is only a temporary arrangement, the concepts we hold as constant, like time and matter, are inherently fleeting. Planets on the brink, worlds that orbit on the edge of black holes. Orbiting near a black hole's photon sphere would shape a planet's days and nights in bizarre ways. The photon sphere is the region where light bends to such an extent that it can orbit in tight circles. Any planet orbiting near this edge would face an intense light show. One side might be locked in a type of endless twilight with strange distortions as the starlight twists around the black hole's gravity. The planet's night side would glow faintly, with light bending around the black hole from the other side. For any observer on the surface, it would be a world where the sky seems to fold in on itself, showing reflections and warped images of nearby stars in every direction. Tidal heating from the black hole's intense gravitational pull would also shape the surface of any planet within close orbit. These forces stretch and compress the planet constantly, similar to how our moon influences Earth's tides, but on a much larger scale. The rock layers would heat up from the inside, fueling active volcanism that could make the entire landscape volatile, with lava lakes and geysers of molten rock constantly erupting. For a world so close to a black hole, tidal heating could even turn its surface into a scorched, molten landscape, only cooling during brief moments of orbital reprieve. Near a black hole, time itself slows down. On these planets, time would move far slower compared to more distant regions of space, a phenomenon known as time dilation. Imagine a few days on the planet being equal to millions of years passing outside the black hole's gravitational influence. Geological changes, atmospheric evolution, and any signs of life would appear frozen or slowed down immensely when viewed from a distance. A planet might take eons to undergo changes that would happen in mere decades elsewhere, creating a suspended world where history itself seems halted. If the planet lacks a star of its own, it could receive its energy from the black hole's radiation. Instead of drawing warmth and light from a sun, planets orbiting near black holes would receive searing radiation emitted from the black hole's accretion disk, the bright hot ring of gas spiraling into the event horizon. This radiation, though intense and potentially deadly to life as we know it, could heat the planet's atmosphere to extreme temperatures. For any hypothetical ecosystems, this energy source would be nothing like the sunlight we depend on, creating environments with potentially toxic atmospheres, fierce winds, and violent radiation storms. In addition to radiation, powerful magnetic fields surrounding the black hole would greatly affect the planet's atmosphere. Many black holes, especially rotating ones, generate intense magnetic fields that can be millions of times stronger than Earth's. This magnetic activity could spark incredible auroras, with the sky lighting up in waves of color. But these magnetic fields could also have severe effects on the planet's weather patterns, constantly interacting with the planet's magnetosphere. The resulting magnetic storms would strip particles from the atmosphere and create dangerous currents within the planet's crust, adding layers of atmospheric and geological turmoil. Any planet close to a black hole faces the pull of the event horizon, the boundary beyond which nothing, not even light, can escape. This region marks the black hole's point of no return, and planets orbiting near it must maintain precise, stable paths to avoid falling in. These orbits are precarious. The tiniest shift could destabilize the planet, sending it spiraling closer to the event horizon. The delicate balancing act between escape and destruction raises questions about how long these edge-orbiting planets might last before gravitational forces win out. Black holes are known to emit high-energy particles at incredible speeds, thanks to processes within their accretion disks. A planet within the vicinity would be bombarded by these rays, similar to how Mars's surface gets hit by solar wind due to its lack of a magnetic field. Over time, this bombardment could erode the atmosphere, while any life or organic compounds on the surface would face severe radiation damage, posing massive challenges for any hypothetical ecosystems. Close proximity to the accretion disk also brings a unique phenomenon: the possibility of an accretion disk-induced atmosphere. If particles from the disk are dense enough, they could form a thin, turbulent atmosphere on the planet. This atmosphere, however, would be vastly different from Earth's, with a composition rich in heavy metals and volatile compounds from the accretion disk itself. Chemical interactions could create peculiar weather patterns with metallic rain and skies tinged by compounds like sulfur or methane, forming weather unlike any we know. Orbiting through the thin outer edges of an accretion disk could also cause atmospheric drag, slowly pulling the planet inward toward the black hole. Over time, this drag could erode the planet's orbit, causing it to inch closer until it ultimately crosses the event horizon. This type of orbital decay, while slow, adds another layer of instability to planets on the edge of black holes. If we could observe one over long periods, we might witness a slow-motion spiral that ends in the planet's final disappearance beyond the event horizon. Scientists wonder if extremophiles could survive on these worlds. Earth's microbes that live in radioactive environments or thrive under high pressures hint at possible survival strategies for life on these extreme planets. These hypothetical organisms might adapt to intense radiation, heavy elements, and constant tidal forces, similar to bacteria found deep within Earth's crust or near hydrothermal vents. Ultraluminous X-ray sources, mystery objects. Ultraluminous X-ray sources, ULXs, pose a challenge to our current knowledge of stellar mechanics. These powerful sources of X-rays shine with luminosities far exceeding typical X-ray emitters, raising significant questions about their origins, mechanics, and the forces powering them. With some ULXs appearing 100 to 500 times brighter than what was once thought possible, they defy the so-called Eddington limit, a theoretical boundary on the brightness of an object powered by accretion. This leads us to ask, what fuels these ULXs, and are the physical laws we thought were absolute actually open to exceptions? Among the most interesting theories put forward by astronomers is the idea that ULXs may have intermediate mass black holes, which are hypothetically situated between stellar mass black holes and the supermassive giants in the heart of the galaxy. Since intermediate mass black holes are able to accrete more material and emit more X-rays, they may be the source of the ULX's extreme luminosity. However, there is no conclusive proof that intermediate mass black holes are the only explanation for ULX, even if they are a strong candidate. New evidence suggests that neutron stars, a completely distinct kind of object, may be responsible for some of these extremely intense emissions in certain instances. In these ULX that appear powered by neutron stars, an extreme process unfolds. Neutron stars and ULX pull matter from a nearby companion star at staggering rates, creating a powerful accretion disk that releases X-rays. This feeding frenzy produces energy levels once thought impossible for neutron stars. sparking theories about ultra-strong magnetic fields that help contain and focus the emission of energy. Pulsing X-ray patterns observed in some ULXs have also led scientists to pinpoint these neutron stars as pulsars, a variety of neutron stars with precise repeating bursts of X-rays. This has led to an entirely new category within ULX, pulsating ultraluminous X-ray sources, or PULXs. The existence of pulses is a fascinating revelation, especially as they are often characterized by powerful magnetic fields, in some cases 1,000 trillion times stronger than Earth's. These magnetic fields are critical because they allow neutron stars to produce pulsations, as the fields constrain the X-ray radiation into beams, which sweep across space as the neutron star rotates. This lighthouse effect is a distinct characteristic of pulsars, a reminder of the incredible power of magnetic fields in shaping the behavior of these cosmic giants. Some astrophysicists have speculated that relativistic jets might be adding to the luminosity of ULX, while neutron stars and intermediate mass black holes are still the most popular theories. These jets, composed of matter being ejected at nearly the speed of light, are not unique to ULXs. They are found around many high-energy astronomical objects, including some black holes and neutron stars. The jets could significantly enhance the apparent brightness of a ULX when they are directed toward Earth, amplifying the luminosity as a result of an effect called relativistic beaming. In other cases, ULXs seem to emit beamed X-rays without the need for such extreme jets. Here, astrophysicists propose that the structure of ULX allows them to channel radiation into focused beams, creating a false impression of an unusually bright source, even if the intrinsic power of the ULX is more modest. This phenomenon, called beamed radiation, remains a contentious topic, but it could offer insight into how these objects defy the Eddington limit without requiring physical properties beyond known parameters. By analyzing their extraordinary accretion rates, which can approach super-Eddington accretion, we can learn more about ULX. We say that accretion rates are super-Eddington if they are more than the theoretical maximum. According to the traditional model of accretion, material colliding with a neutron star or black hole generates radiation that, up to a point, should repel material instead of attracting it. As far as we can tell, ULX are able to accrete matter at much greater rates than this limit allows, most likely due to accretion disks. Astronomers can learn more about the role of intense accretion in the formation and maintenance of ULX by analyzing these patterns. The fact that ULX are more common in low metallicity galaxies like the Magellanic Clouds is one of the things that makes them so enigmatic. This might mean that metal-poor environments favor the formation of ULXs, suggesting that chemical composition plays a role in shaping the evolution of stellar objects in ways we're only beginning to understand. Low metallicity galaxies could provide fuel-rich environments where ULXs can persist, with metal-poor gas making it easier for compact objects to accrete material without hindrance. Things become much more complicated since ULX emissions include both optical and ultraviolet light. ULX are defined by their ultraluminous X-ray emissions, yet many also shine in ultraviolet and optical wavelengths, suggesting diverse energy sources or complex interactions within the accretion disk. This multi-wavelength emission is an important fingerprint of ULXs, and researchers use it to differentiate ULXs from other high-energy sources. Since many ULXs are located in star-forming regions where accretion fuel is more abundant, they also provide light on the structure and development of the galaxy. By observing ULX within these regions, scientists are offered a window into the lives of binary stars, dense gas clouds, and other critical elements that shape a galaxy's evolution. ULX indicate active and extended bursts of high-energy radiation by surrounding themselves with enormous ionized gas bubbles. These superbubbles can be hundreds of light-years in diameter, evidence of a ULX's influence on nearby stars, gas clouds, and interstellar material. These interactions shape the local environment, producing vast bubbles that mark the presence and power of ULX. Quasi-periodic oscillations, or QPOs, are another intriguing property of some ULX, where the brightness of the object fluctuates rhythmically. These oscillations point to dynamic interactions within the accretion disk, potentially arising from periodic changes in the disk's structure or from material orbiting close to a neutron star or black hole. QPOs hint at the incredible gravitational forces shaping ULX, forces so extreme they may even warp spacetime. The magnetic fields in some ULXs are reminiscent of magnetars, neutron stars with ultra-strong magnetic fields that can emit bursts of energy far beyond what most neutron stars produce. ULXs displaying these magnetar-like properties may represent a new type of hybrid star, one that exhibits features of both pulsars and magnetars. These magnetic fields also play a role in the emission patterns of ULX, with beams of X-rays sweeping across the sky and producing pulsations that have been a key signature in identifying pulks. The instability of accretion disks in ULXs means that their emissions often show variability, with bursts of X-rays interspersed by quieter periods. This unstable behavior reflects the challenges of maintaining such extreme accretion processes over time and suggests that many ULXs may have life cycles of activity and dormancy. The significance of ULXs in comprehending cosmic backdrops is also substantial. They add to the X-ray background a subtle yet pervasive X-ray light that permeates the cosmos. ULXs help fill gaps in our knowledge about the sources of this background, showing how many galaxies host these powerful emitters that add to the general high-energy glow of the cosmos. Some ULXs may be relics of failed supernovae, according to contemporary astronomical speculation. In some cases, the star may collapse into a black hole without producing an enormous supernova explosion. Such objects would have accretion rates much higher than those of standard black holes, potentially contributing to the extreme luminosities observed in ULX. Rare gamma-ray emissions from a small number of ULX raise the possibility that these objects share properties with gamma-ray bursts, among the most powerful cosmic phenomena. The prospect that ULXs could generate gamma-ray bursts hints at the potential for violent high-energy activity, further linking them to other extreme cosmic events. The most extreme ULX might even distort time in their immediate surroundings due to their strong gravitational fields. Time dilation, an effect predicted by Einstein's theory of general relativity, could mean that the passage of time near a ULX differs from that in distant regions of space. Such effects highlight the potential of ULXs to test and refine our understanding of relativity. In the hunt for X-ray binaries, in which a neutron star or black hole interacts with a partner, ULXs are intriguing objects due to their unique characteristics. The influence of ULXs can even extend to their surroundings, as they act as hidden engines in galaxies, creating energy flows and structures that influence galactic dynamics. As they emit intense X-rays, ULXs can also shed light on how dust and gas behave under extreme radiation. ULX interacting with dust release infrared emissions, revealing information about interstellar material and cosmic radiation absorption patterns. By studying these infrared emissions, scientists gain a better understanding of the intricate relationship between ULXs and their environments. All things considered, ULX are a place where the limits of contemporary astrophysics are being pushed by a combination of gravitational forces, magnetic fields, and accretion processes. With mysteries ranging from their origins to their extraordinary luminosity, ULXs challenge scientists to explore new physical regimes and question the limits of what compact objects in the universe can achieve. The cold spot. Anomaly. Is it a glitch or evidence of another universe? The cold spot anomaly stands out as one of the most intriguing phenomena in modern cosmology. It manifests as a region in the cosmic microwave background, CMB, that appears cooler than its surroundings, located roughly 1.8 billion light-years away from Earth. This anomaly has caught the attention of scientists and enthusiasts alike, sparking debate and investigation into its origins and implications for our understanding of the universe. Located within the CMB, the cold spot spans an impressive 1.8 billion light-years, making it one of the largest known anomalies of its kind. Its discovery can be traced back to the Wilkinson Microwave Anisotropy Probe, WMAP, which began its mission in 2001. WMAP's data revealed slight temperature fluctuations in the CMB, with the cold spot standing out due to its significant drop in temperature compared to the surrounding areas. Later, the Planck satellite, launched by the European Space Agency, confirmed these findings, providing further insight into this mysterious region. What makes the cold spot particularly perplexing is its unexpected nature within the framework of the standard cosmological model. This model predicts a nearly uniform distribution of temperature across the universe with only minor fluctuations. However, the cold spot presents a challenge to this notion as it defies the expected statistical distribution of temperature variations in the CMB. This raises questions about the processes that shaped the early universe and the mechanisms behind cosmic structure formation. A prominent theory proposes that a huge cosmic emptiness may be the culprit responsible for the cold spot. Such voids are vast regions of space that contain far fewer galaxies and dark matter than the average region. In theory, as photons travel through a void, they can lose energy, leading to a cooler temperature in the CMB, known as the integrated Sachs-Wolf effect. However, researchers have found that even the largest known voids cannot fully account for the magnitude of the cold spot, indicating that additional factors may be at play. Despite its attractiveness, the void hypothesis has some problems. According to new research, the cold spot can't be explained by a cosmic emptiness alone, since its features are too prominent. The gravitational influence of structures such as superclusters and filaments may also play a role, but they cannot completely explain the observed temperature drop. The scientific community remains divided on this issue, leading to ongoing debates about the anomaly's origins. The enigma of the cold spot is being investigated further, and some experts have begun to consider the possibility of several universes. This theory posits that our universe is just one of many, each with its own distinct physical laws and properties. In this context, the cold spot could be viewed as evidence of a bruise left behind by a collision with another universe. The possibility of such a collision raises profound questions about the nature of reality and the structure of space-time. When we consider the cold spot as a relic of a bubble universe collision, we get the concept of cosmic inflation, which states that early on in the universe, space expanded exponentially. If the cold spot were a result of such a collision, it would suggest that the universe's initial conditions were more complex than previously understood. This could lead to significant revisions in our theories about cosmic evolution. Another interesting angle is the potential role of quantum fluctuations in the early universe. These fluctuations could result in the uneven distribution of matter and energy, contributing to the cold spot's formation. By examining the interactions between particles during the universe's infancy, scientists hope to gain a better understanding of how these anomalies arise and evolve over time. Evaluation of the cold spot's relevance to cosmology as a whole relies heavily on statistical analysis. Studies indicate that the likelihood of encountering such a pronounced anomaly in the current model of the universe is between 1% and 2%. This rarity suggests that the cold spot may not be a mere statistical fluke, but rather a genuine feature that challenges our understanding of cosmic structure. Moreover, the cold spot's temperature fluctuations contribute to deviations in the CMB's power spectrum, which is a representation of temperature variations across the sky. Ideally, this spectrum should follow a predictable pattern, but the cold spot introduces anomalies that invite further investigation. Scientists are keen to explore how these fluctuations could influence our understanding of dark matter and dark energy, two of the most enigmatic components of the universe. The possible impact of cosmic superstructures on the temperature of the cold spot is another intriguing topic. Massive structures, such as galaxy clusters and superclusters, exert gravitational forces that can affect the paths of photons traveling through the universe. While the role of these structures in shaping the cold spot remains an open question, their potential impact is an intriguing line of inquiry. In their exploration of the cold spot, scientists are also looking for evidence of dark flow, which might be caused by gravitational forces from places outside of our visible universe and indicate that galaxy clusters are traveling in a certain direction. The connection between the cold spot and dark flow could provide valuable insights into the dynamics of cosmic structures and the gravitational interplay between galaxies. Much of the debate over the cold spot has moved into theoretical physics, where it affects cosmological and gravity theories. Some researchers propose that the anomaly's existence may necessitate revisions to our current understanding of gravity, particularly in the context of large-scale cosmic behavior. These considerations underscore the importance of the cold spot as a catalyst for new ideas and discussions within the scientific community. In parallel, ongoing observational campaigns continue to enhance our understanding of the cold spot. Improved instruments and telescopes allow scientists to gather more precise data, which may lead to new revelations about this enigmatic region. As technology advances, researchers hope to capture more detailed images and measurements of the CMB, enabling them to investigate the cold spot and its potential connections to other cosmic phenomena. A number of scientific fields come together in the cold spot anomaly, such as theoretical physics, cosmology, and astrophysics. Its presence invites discussions about the fundamental nature of the universe, the structure of space-time, and the possibilities of multiverse theories. As scientists continue to explore this mysterious region, they remain vigilant, open to new discoveries and ideas that could reshape our understanding of the cosmos. This anomaly represents a significant opportunity for scientists to challenge existing paradigms, encouraging a reevaluation of our models of the universe. The interplay between observational evidence, theoretical models, and emerging technologies will shape the future of research into the cold spot and its implications for our understanding of the universe. Rogue black holes. Wandering giants. Rogue black holes are known as silent travelers. Unlike black holes confined to galaxies, these wander through the vast spaces between, unconnected to any specific star system. The reason? Ejection events. When two massive stars orbiting each other explode as supernovae, one black hole can get flung away by intense gravitational forces. Similarly, galactic collisions or close interactions with other celestial giants can propel black holes into a life of solitary wandering. Each rogue black hole leaves behind its host galaxy, becoming a quiet wanderer in interstellar or even intergalactic space. These silent journeys aren't leisurely strolls. Rogue black holes travel at speeds reaching millions of miles per hour. Ejection forces, like those in galaxy mergers or violent stellar deaths, launch them on paths that can last billions of years, untouched by any galactic pull. As they pass through space, they become ghost-like, almost impossible to detect due to their immense speeds and lack of interaction with light. These high velocities make them elusive, hidden from sight, and unlikely to be detected unless we catch them in specific rare moments. Unlike stars or planets, rogue black holes cannot be detected by any emitted light. They are, after all, the ultimate cosmic vacuums, absorbing everything within their gravitational reach without releasing anything detectable by our telescopes. In the silent voids of space, a rogue black hole moves through without consuming surrounding gas or dust that might reveal its presence. Without the benefit of illumination, astronomers struggle to detect these hidden wanderers and rely mostly on gravitational effects when possible. When rogue black holes approach star systems, they become agents of disruption. Their intense gravitational pull distorts the orbits of stars, planets, and anything nearby. This disturbance can throw planets out of their orbits or destabilize entire star systems, leaving celestial bodies unmoored and at risk of drifting away or being pulled into the black hole itself. In the worst case, a planet or star could be entirely consumed, adding to the black hole's mass and power. These quiet giants leave destruction in their wake, reshaping the structure of the systems they pass through. Our solar system might be in danger from renegade black holes, which is one of the most terrifying possibilities. Although the chances of an errant black hole crashing into our area are low, they are not zero. A near encounter may easily disrupt the orbits of the Sun, moons, and planets, leading to planetary chaos. Near-Earth encounters have the potential to evict planets from our solar system, sending them hurtling into icy, dark solitude. Scientists speculate that many rogue black holes may have formed in the early universe, during a time when massive stars lived short, violent lives before collapsing into black holes. Some of these stars, situated on the outer edges of galaxies, may have died in explosions that launched their black hole remnants into space, unconnected to any galactic anchor. Billions of years later, these primordial rogue black holes may still be traveling through the cosmos, relics of a time when the universe was young and turbulent. Rogue black holes could potentially host planets of their own, though this idea seems counterintuitive. Under certain conditions, a rogue black hole could gather enough surrounding gas and dust to form small planetary systems, with the planets orbiting the black hole as it travels. These theoretical dark systems would move quietly, completely isolated, without the warmth or light of a star, creating a unique cosmic arrangement unlike any typical solar system we know. It's a notion that challenges what we think of as habitable zones and stable planetary systems. Finding these evasive things is a real challenge. Gravitational microlensing is one of the few methods via which rogue black holes have been detected by astronomers. The gravitational pull of a rogue black hole causes a star far away to temporarily seem magnified when it passes in front of it. Gravitational microlensing is a powerful method for detecting rogue black holes since it gives a peek of their positions before they continue their quiet voyage. But even with this strategy, sightings are still very unusual and difficult to forecast. Astronomers have recently detected possible rogue black holes within the Milky Way's halo, the vast region surrounding our galaxy. These objects were found not through direct observation, but by measuring gravitational interactions on surrounding stars and gas. The Milky Way itself may host several rogue black holes drifting within its outer regions, posing potential risks to the stability of nearby stars or star clusters. Their presence in our own galaxy is a stark reminder that rogue black holes aren't limited to distant galaxies. They could be closer than we realize. Their possible role as gravitational wave generators is another intriguing feature of renegade black holes. As they merge or circle each other, black holes, particularly those with binary pairs, emit ripples in spacetime. Observatories on Earth have found gravitational waves, which offer another clue about the whereabouts and behavior of rogue black holes. More information about the abundance and behavior of these enigmatic objects throughout the cosmos may be uncovered by this wave discovery, which paves the way for future research. When galaxies collide, supermassive black holes at their centers can interact, sometimes leading to ejection as forces reach extreme levels. These ejected black holes then travel across intergalactic distances, free from any host galaxy, becoming some of the most massive rogue black holes in existence. These events contribute to the growing population of rogue black holes, scattered like cosmic shrapnel in the aftermath of galactic collisions. In a poetic sense, rogue black holes could be seen as the ghosts of absorbed or dismantled galaxies. When larger galaxies consume smaller ones, the black holes from these smaller galaxies may get ejected, drifting away from the newly merged galaxy. These wandering black holes become a sort of cosmic afterimage, traveling alone as remnants of lost galaxies. They are living records of galactic evolution, carrying with them the history of their lost homes. Calculating the trajectory of a rogue black hole is an incredibly difficult task, as each gravitational interaction, no matter how small, could alter its path over millions of years. This unpredictability keeps astronomers guessing about where they might be heading and whether they might eventually cross paths with other galaxies, star clusters, or perhaps even regions of space that challenge our current understanding of cosmic dynamics. Adding another layer to their intrigue, rogue black holes may have a surprising connection to the dark matter puzzle. Some scientists speculate that primordial black holes from the early universe could account for a small fraction of dark matter, the elusive substance that makes up most of the universe's mass. The idea of rogue black holes as massive bullets drifting through space captures the danger they pose. While not moving with intent, their mass alone gives them the power to alter anything in their path, from individual stars to entire star clusters. Some rogue black holes reach masses millions of times greater than the Sun, with gravitational forces strong enough to consume or disturb vast swaths of space. Rogue black holes vary greatly in size and mass. They can be as small as stellar mass black holes, remnants of collapsed stars, or as massive as supermassive black holes ejected from galaxy cores. This range means that rogue black holes are diverse in both origin and impact, adding layers of unpredictability to their already mysterious nature. Gamma-ray bursts, GRBs, rare cosmic explosions. Gamma-ray bursts, known for releasing staggering amounts of energy, are some of the most powerful events in the universe. These flashes can emit more energy in seconds than our Sun will produce in its entire lifespan. But while scientists know much about their intensity, the specifics behind GRBs remain mysterious, as each discovery adds new complexity to what we know about the cosmos. Each burst begins with a sudden explosion of energy. This release happens in two main forms, long and short bursts. Long bursts lasting over 2 seconds are typically linked to the collapse of massive stars, events we call supernovae. When these stars exhaust their fuel, they collapse into black holes, and the energy released creates these long gamma-ray bursts. On the other hand, short bursts, which last less than 2 seconds, often come from collisions of neutron stars. While these two categories might sound straightforward, scientists have discovered certain GRBs that do not neatly fit into either, suggesting there may be other undiscovered sources for these powerful events. Magnetic spin-downs are one theory that complicates our current understanding of brief bursts. As their revolution slows down with time, magnetars, neutron stars with extremely high magnetic fields, emit bursts of energy. Even though it's not common, this idea provides an explanation for some GRBs that don't seem to come from the usual places. Neutron star collisions or supernovae. It suggests that there could be other ways that these powerful explosions might happen. The energy released in a single GRB is difficult to comprehend. For context, a hypernova, an explosion of a star much larger than the Sun, produces a tremendous amount of energy, much greater than a typical supernova. Some GRBs are thought to originate from hypernovae, and these bursts can outshine entire galaxies, albeit briefly. When we detect a GRB, it's often from vast distances, as these events are rare and can happen anywhere across the universe. Yet despite these distances, the brightness of GRBs allows us to observe galaxies billions of light-years away, effectively using GRBs as beacons to peer into the distant reaches of space. Some gamma-ray bursts reach us from early periods in the universe's history, more than 13 billion light-years away. These ancient GRBs offer a unique glimpse into the cosmos during its formative years, providing data on what the universe looked like shortly after the Big Bang. By studying these distant bursts, scientists gain clues about the early stages of galaxy formation and the types of stars that existed when the universe was still young. GRBs also reveal insights about the materials around them through something known as the fireball model. According to this model, when particles accelerate to nearly the speed of light in a confined area, they create the intense light and afterglow associated with gamma-ray bursts. This model helps explain the appearance of GRBs and provides a framework for understanding how the energy within the burst is dispersed. The afterglow is particularly important to astronomers because it allows them to study the region around the burst, often giving clues about the structure and composition of space near these violent explosions. Their X-ray spectral afterglow is another intriguing feature of GRBs. An X-ray radio wave or even visible light afterglow of reduced energy remains after the main flash has gone out. Theoretically, after a GRB finishes, a black hole stays at its core, devouring surrounding material and emitting energy that may be detected in the X-ray spectrum. This is how many scientists explain these afterglows, which they see as evidence of black hole development. In addition to linking GRBs to the development of black holes, this theory also offers a workable approach to studying the latter phases of these massive explosions. Due to their incredible brightness, astronomers can use them as reference points or beacons to study the structure of space between galaxies. By observing how GRB light travels through intergalactic space, researchers can infer details about the universe's structure and test theories on dark matter and dark energy, two of the universe's most elusive components. In this way, GRBs indirectly contribute to our understanding of the universe's large-scale structure. The light from some GRBs is polarized, adding yet another layer of complexity. This polarization suggests that the burst travels through a magnetic field, hinting at the conditions surrounding the GRB source. By analyzing polarized light, scientists gather information on magnetic fields and how they interact with high-energy particles, offering new perspectives on the environments that produce these bursts. It's worth noting that GRBs aren't just curious flashes of light from afar. They have implications for life in the universe as well. If a gamma-ray burst were to occur close to Earth, it could potentially strip away the ozone layer, exposing the surface to harmful ultraviolet radiation from the sun. This process would dramatically affect the planet's climate and could pose serious risks to life. Fortunately, such bursts are rare, and the odds of one happening near Earth are low. However, this possibility places GRBs among the few cosmic phenomena with the potential to impact life on our planet. Some scientists propose a link between GRBs and another type of cosmic phenomenon, fast radio bursts, FRBs. FRBs are intense but brief bursts of radio waves, and while their exact origin is still under debate, some researchers speculate they might be connected to GRBs or similar high-energy events. This connection remains a topic of research as scientists work to determine whether these two types of phenomena share common origins or physical processes. The structure of gamma-ray bursts is another area of ongoing research. GRBs often involve jets of high-speed particles ejected from collapsing stars. These jets are crucial to understanding GRBs but remain difficult to study due to their transient nature. Different GRBs exhibit variations in jet structure, and researchers are still trying to determine how these differences arise and what they might reveal about the underlying physics. Among the peculiarities of certain GRBs is an occurrence known as a light echo. A type of reflection or echo of the original burst can be produced when the afterglow of a GRB interacts with gas or dust in the vicinity, but only under specific circumstances. These echoes provide us a rare glimpse into the event's context and prolong our observations of the GRB. Studying these echoes gives astronomers more information about the dust and gas characteristics in those faraway places. GRBs also leave distinct imprints in the gamma-ray spectrum, almost like cosmic fingerprints. Each burst has a unique energy signature that allows scientists to categorize it and compare it to other bursts. By analyzing these patterns, researchers can identify specific characteristics of the burst and, in some cases, deduce details about its origin. This fingerprinting process has proven essential for differentiating between types of GRBs and understanding the variety of events that can produce these bursts. In densely populated star clusters, GRBs could potentially strip atmospheres from nearby planets, making these regions inhospitable to life. This influence is especially relevant when studying star systems with high-mass stars prone to explosive ends, as these systems are more likely to produce gamma-ray bursts. The impact of a GRB in such environments demonstrates the potential of these bursts to shape the habitability of entire regions in space. The redshift measurements associated with GRBs provide further insights into the nature of our expanding universe. As the universe expands, the light from distant objects stretches, a phenomenon known as redshift. By measuring the redshift of GRBs, scientists gather information on how quickly the universe is expanding and gain clues about dark energy's influence on cosmic expansion. Through these measurements, GRBs contribute to our understanding of the universe's growth and evolution over time. GRBs contribute to the formation of heavy elements, including rare elements like gold and platinum. When neutron stars collide and create a gamma-ray burst, they scatter these heavy elements into space, enriching future star systems. This process is one way that planets, including Earth, come to contain these valuable materials, as they are born from the remnants of past explosions. Solar dimming, when the sun's output dips. Across our planet, sunlight fuels life as we know it, driving processes as vital as photosynthesis and climate regulation. However, the phenomenon of solar dimming, or the gradual decrease in sunlight reaching Earth's surface, suggests that this essential light may not always be constant. Factors behind solar dimming are both naturally occurring and human-made, with pollution playing a significant role in scattering sunlight, especially in heavily industrialized regions. Over the last several decades, areas like Asia and Europe have felt the effects of dimming more intensely, with regional shifts tied directly to human impact. The causes of solar dimming reveal the significant role of aerosols, including sulfates, dust, and black carbon, which are byproducts of industrial pollution. These particles enter the atmosphere, creating a barrier that reflects and scatters sunlight, preventing it from fully reaching Earth's surface. While dimming happens on a global scale, local effects vary widely. In countries like India and China, where industrial activity and pollution have increased significantly, thick smog blocks sunlight over urban areas, creating a visible dimming effect in the skies above. This reduction in sunlight doesn't just change the appearance of our skies, it impacts agriculture as well. Crops rely on a predictable amount of sunlight for optimal growth, and dimming throws this delicate balance off. Plants, limited in the light they can use for photosynthesis, struggle to produce as much food and oxygen. Reduced sunlight means lower yields and diminished crop quality, which in turn affects the broader food supply. As certain regions experience stronger dimming effects, this adds another layer of complexity to food security issues worldwide. One of the most surprising aspects of solar dimming is its effect on global warming. Paradoxically, solar dimming may temporarily mask some of the warming effects caused by greenhouse gases. The layer of pollution that contributes to dimming also cools the planet by preventing sunlight from penetrating fully, an effect called global cooling. However, this is only a temporary relief. Reducing emissions from aerosols would reveal the true extent of climate change caused by greenhouse gases, leading to a sudden and sharp rise in global temperatures. This masking effect makes it harder for scientists to predict the full impact of warming, as dimming and climate change interact in complex and sometimes contradictory ways. Potential solution scientists have discussed is geoengineering, the intentional manipulation of Earth systems to counteract climate change. Some researchers believe that artificially increasing solar dimming by introducing aerosols into the atmosphere could provide a temporary solution to combat rising temperatures. Yet the ethical and environmental risks of geoengineering are significant, with possible unintended consequences for ecosystems, weather patterns, and even human health. In certain parts of the world, dimming has already started to disrupt traditional rainfall patterns. As sunlight decreases, it affects how much moisture the atmosphere can hold, impacting weather cycles. This disruption is particularly evident in regions with monsoon systems, where solar dimming can contribute to either delayed rainfall or droughts, directly affecting communities dependent on seasonal rains. Changes in rainfall due to solar dimming are not limited to monsoon regions, but can be felt globally as they cascade through connected atmospheric systems, potentially influencing everything from local storms to larger climate events. The Asian brown cloud is a thick layer of pollution that covers most of South Asia, including both urban and rural areas, and is a clear illustration of localized dimming. Coal plants, cars, and agricultural fires are the main contributors to this haze's composition of dust, soot, and other contaminants. Lower temperatures and less rainfall over South Asia have been associated with the Asian brown cloud, which filters sunlight and affects millions of people. Everyday living, agricultural production, water supply, and climate are all impacted by this persistent smog. Beyond its impact on climate, solar dimming also has unexpected effects on extreme weather events. The cooling effect in specific regions, caused by a reduction in solar energy, has created pockets of atmospheric disturbance that influence the intensity of storms. For instance, altered temperature balances in certain areas can fuel stronger hurricanes and typhoons, which then carry their energy to other parts of the world. Scientists continue to explore this connection, analyzing how dimming impacts extreme weather and what it means for global weather patterns. Human health can also be affected by solar dimming, as it leads to reduced sunlight exposure, which is essential for vitamin D synthesis in humans. In regions experiencing heavy solar dimming, people may not receive adequate sunlight exposure, leading to a potential rise in vitamin D deficiencies. This deficiency impacts bone health, immune system functioning, and overall well-being, especially among populations that already face limited sunlight due to climate or lifestyle. Vitamin D deficiency has also been linked to mood disorders, meaning that the effects of dimming extend beyond the physical, impacting mental health as well. Solar dimming isn't entirely irreversible. Since the 1990s, some regions have observed a shift known as global brightening, as cleaner air regulations have reduced the number of aerosols in the atmosphere. For example, Europe, after implementing stricter air quality standards, has seen a reduction in solar dimming. This reversal offers a glimpse of hope that with sustained efforts, dimming could lessen globally, allowing natural light levels to return to more stable norms. The effects of dimming extend even to our modern technology. Solar power systems, which rely on consistent sunlight, have seen reduced efficiency in areas with significant dimming. Solar power, heralded as a solution to carbon-based energy, depends on sunlight, and dimming has slowed production rates in specific regions, challenging the sustainability of solar energy sources and the push toward renewables. Dimming also causes temperature discrepancies between Earth's surface and upper atmosphere. While surface temperatures might drop due to dimming, the upper atmosphere can retain heat, creating an imbalance that affects cloud formation and overall weather stability. These temperature gradients are studied to understand how dimming might be leading to unique weather events and unexpected climate shifts. Stalagmites are used by scientists to monitor patterns of dimming that span millennia. Researchers learn about the evolution of dimming over millennia by examining mineral deposits in these cave formations, which reveal the history of sunlight reaching Earth's surface. Rates of glacier melt also provide information on solar darkening. The melting of glaciers has slowed in certain areas where temperatures have dropped because of dimming, but in others, where air pollution is decreasing and sunshine is increasing, the melting of glaciers is progressing at a quicker rate. Dimming and glacial health interact in a way that shows how reducing pollution might have unanticipated consequences of speeding up the warming process. Throughout history, solar dimming has fluctuated, with evidence found in ice cores that reveal periods of intense dimming caused by volcanic eruptions or human activities. Volcanic eruptions like Krakatoa or Mount Pinatubo release vast amounts of ash and sulfur, leading to temporary dimming and global cooling events that can last for years. Such natural instances of dimming give scientists valuable models to understand human-caused dimming today. The relationship between solar dimming and oceanic circulation is another area of study, as dimming changes the temperature balance between air and sea. This temperature difference affects currents and can influence the distribution of warm and cold waters, impacting marine life and weather patterns across continents. Changing ocean currents alter ecosystems, causing shifts in fish populations and affecting economies dependent on marine resources. Climate scientists now factor solar dimming into long-term climate models, understanding that dimming's cooling effects can mask true global warming. These models are essential to accurately predict climate futures, as dimming is only one of many variables in the complex web of Earth's systems. By accounting for dimming, scientists can better assess the risks and trajectories of climate change, ensuring a clearer understanding of what the future holds. Contrails from airplanes create high-altitude clouds that trap sunlight and contribute to dimming. As global travel increases, these clouds play a small but noticeable role in the overall dimming effect, prompting scientists to examine how high-altitude pollutants might influence the larger climate system. With each new study on solar dimming, it becomes clearer that humanity's actions are woven into the climate's fabric in ways we're only beginning to comprehend. The story of solar dimming is a reminder that while natural forces shape our world, human decisions can amplify or mitigate these forces. Wandering stars, stellar nomads. Observations of wandering stars have intrigued humanity for centuries. These celestial bodies which wander across our night sky defy the typical notion of stars being fixed in their places. Historically, they captivated ancient civilizations who interpreted their movements in various ways. For instance, the ancient Greeks observed these wanderers and called them planets, a term derived from the Greek word for to wander. This understanding laid the groundwork for modern astronomy, revealing the dynamic nature of our universe. Wandering stars are more than just planets. They have played a pivotal role in shaping humanity's understanding of time and navigation. In ancient societies, the movements of these stars were closely monitored, allowing people to create calendars and predict seasonal changes. For example, the rising and setting of Venus in the sky was crucial for agricultural societies, signaling the best times for planting and harvesting. This close relationship between wandering stars and human activity showcases how our ancestors used the cosmos as a guide for everyday life. Retrograde motion is an unusual feature of wandering stars. They seem to change directions from time to time, deviating from their usual trajectory across the sky. Significant progress in astronomical theory was spurred by this perplexing tendency. Ptolemy and other early astronomers had a hard time making sense of this occurrence, since it ran against the widely held notion that the motion of the heavens was constant and predictable. As a result of Copernicus's heliocentric model, our view of the cosmos was drastically altered, and retrograde motion finally had a reasonable explanation. The study of these stars has provided astronomers with essential tools for discovering exoplanets, planets outside our solar system. By observing how a star's light dims when a planet passes in front of it, researchers can identify these distant worlds. This method, known as the transit method, has led to the discovery of thousands of exoplanets, significantly expanding our knowledge of the universe and its potential for hosting life. Gravitational effects of wandering stars like Jupiter and Saturn help maintain the balance of our solar system. These massive planets influence the orbits of smaller bodies, including asteroids and comets. Jupiter, in particular, acts as a shield for Earth, attracting or deflecting potential threats from the outer solar system. This protective role underscores the importance of these wandering stars in safeguarding our planet from cosmic hazards. Research into wandering stars can shed light on the mechanisms that control the birth of planets. The evolution of solar systems can be better understood by studying the paths taken by these stars and the traits they exhibit. We can learn more about the cosmic circumstances that gave rise to our solar system by studying the interactions between roving stars and the settings in which they reside. Historically, the motion of wandering stars played a vital role in the evolution of astrology. Ancient cultures believed that the positions of these celestial bodies influenced human destiny. For instance, the Greeks and Romans associated each wandering star with specific deities, shaping their mythology and impacting their worldview. These beliefs connected human experiences with cosmic events, illustrating how intertwined our lives are with the universe. The different atmospheres of wandering stars are another thing that scientists and fans are interested in. The atmosphere of a planet determines its surface features and the likelihood of life thereon. Mars, with its thin atmosphere, provides a striking contrast to Venus's thick atmosphere, which traps heat and causes the planet to be extremely cold. Planetary development and the possibility of habitability on other worlds can be better understood by observing these distinctions. Navigational practices in ancient times were also significantly influenced by wandering stars. Sailors and explorers relied on the predictable paths of these celestial bodies for navigation. The positions of planets like Venus and Mars served as guideposts for mariners, helping them chart their courses across the vast oceans. This celestial navigation highlights the profound connection between humanity and the cosmos as we've looked to the skies for direction for millennia. The phenomenon of eclipses, where wandering stars pass in front of or behind other celestial bodies, has captivated observers throughout history. Ancient civilizations often recorded these events, leading to a deeper understanding of the mechanics of celestial bodies. Predicting eclipses required meticulous observations of wandering stars, showcasing the blend of art and science in early astronomy. The ability to foresee such occurrences allowed societies to prepare for significant cultural and religious events, reinforcing the impact of these celestial phenomena on human history. Their role in navigation and timekeeping, wandering stars have sparked cultural and mythological narratives throughout the ages. Many cultures have woven stories around these celestial wanderers, often attributing various traits and behaviors to them. The tale of the morning star, for example, is prominent in many mythologies, symbolizing hope and new beginnings. These narratives reflect humanity's desire to find meaning in the cosmos and connect our existence to the vast universe. Recent scientific discoveries have clarified the processes that cause wandering stars to develop and their possible origins. The formation of stars, according to research, typically takes place in areas with high concentrations of gas and dust, where the forces of gravity bring together various forms of materials. Research into star formation has shown that many stars on the move develop in clusters while they are young, but gradually drift apart as they get older. Both the intricacy of the structure of the cosmos and our knowledge of star evolution are enhanced by this process. Wandering stars also offer insights into the future of our solar system. As they interact gravitationally, their orbits can shift over millions of years. This ongoing dance of celestial bodies can lead to significant changes in the architecture of our solar system, potentially affecting the orbits of Earth and other planets. Understanding these dynamics is crucial for predicting future events and preparing for potential challenges. Observing wandering stars provides a glimpse into the history of our universe. The light we see from these stars carries information about their past, allowing scientists to study the universe's evolution. By analyzing the light emitted from wandering stars, researchers can determine their composition, age, and the processes that led to their formation. This quest for knowledge about the cosmos connects us to our origins and inspires curiosity about the vast unknown. With the development of powerful telescopes and observational techniques, astronomers can now explore previously inaccessible regions of space. The search for wandering stars in other solar systems has become an exciting frontier in astronomy, leading to new discoveries and a deeper appreciation for the complexity of our universe. Their movements inspire curiosity, reveal the intricate processes of stellar evolution, and deepen our understanding of the universe. Galactic cannibalism. When galaxies collide, chaos ensues. Galactic cannibalism is a fascinating and complex phenomenon that goes beyond mere cosmic events. It reflects the intricate dynamics of galaxies and poses significant implications for human civilization. As galaxies merge and consume one another, the processes that unfold can serve as a mirror for our own societal behavior, survival strategies, and environmental concerns. As galaxies collide and merge, they often eject materials into the intergalactic medium. These materials can contribute to the formation of new star systems over billions of years. This process highlights an essential link between the vast universe and our planet. It raises questions about how these cosmic occurrences might influence the development of life elsewhere in the universe and even our own solar system. Could the ingredients for life be spread throughout the cosmos, thanks to the remnants of these galactic mergers? Throughout history, humans have interpreted cosmic events as signs or omens. The impact of these events can be seen in ancient cultures, where celestial occurrences influenced mythology, literature, and art. The chaotic nature of galactic cannibalism serves as a powerful metaphor for human conflicts, where societies consume resources and power in a bid for survival. This reflection prompts us to consider how our actions resonate not only within our communities, but also across the globe. Humanity has made tremendous advancements in technology. The study of galactic cannibalism has led to the detection of gravitational waves generated by the mergers of galaxies and their supermassive black holes. Instruments like LIGO have been pivotal in this regard. These waves provide critical insights into the behavior of the universe and challenge our understanding of physics. This intersection of cosmic phenomena and human technology serves as a testament to our curiosity and desire to explore the unknown. Resource scarcity is a pressing issue faced by human societies, often driven by overconsumption and environmental degradation. The concept of galactic cannibalism can illuminate these challenges, reminding us of the cycles of consumption and growth that dominate our planet. As galaxies devour one another for resources, we too must consider sustainable practices to ensure that we do not deplete our own resources. This awareness can inspire a more mindful approach to our consumption patterns, reflecting the need for a balance between growth and sustainability. Galactic cannibalism also serves as a cautionary tale. The violent nature of galaxy mergers demonstrates the consequences of unchecked growth and consumption. As larger galaxies consume smaller ones, the potential for collapse becomes apparent. This warning resonates deeply with contemporary societies facing environmental crises and geopolitical conflicts. It highlights the importance of fostering a culture of collaboration and responsibility rather than competition and greed. Another appealing component of galactic cannibalism is the interconnection of cosmic events. Similar to how galaxies are affected by the gravitational pull of nearby galaxies, human cultures are intricately linked. The consequences of an action in one area can ripple throughout the globe. In light of this knowledge, it is clear that urgent problems such as poverty, resource management, and climate change necessitate international collaboration. The key to finding solutions that work for everyone is realizing how interdependent we are on one another. As galaxies consume one another, they can trigger the formation of new stars and planets, creating potential environments for life. This possibility fuels our curiosity and hope for discovering extraterrestrial life. The exploration of these cosmic processes reminds us of our place in the universe and prompts philosophical questions about existence and the nature of life. The search for life beyond Earth is not just a scientific endeavor. It also compels us to reflect on our responsibility to protect our planet and its resources. There are far-reaching consequences for our knowledge of the cosmos and ourselves brought about by the technical developments that enable us to examine cosmic phenomena like galactic cannibalism. We are always reassessing our role in the universe in response to new discoveries. We can learn a lot about human nature, social hierarchy, and resource allocation from what we discover about galactic dynamics. Galactic cannibalism also brings forth ethical implications. As we deepen our understanding of the universe and its complex processes, we are faced with questions about our responsibilities towards our planet and each other. This ethical reflection can influence humanitarian efforts and environmental stewardship, urging us to take action to protect our shared home. In education, the study of galactic cannibalism provides a rich opportunity for engaging young minds. It sparks interest in astrophysics and environmental science, encouraging future generations to explore the universe and understand the delicate balance of our ecosystems. The idea of one galaxy consuming another can serve as a lens through which we examine human behavior, power dynamics, and survival instincts. This reflection can provide valuable insights into our historical patterns of growth and collapse, prompting discussions about how societies can learn from the cosmos. The lessons learned from galactic cannibalism may offer guidance. The study of larger systems and their interactions can inform our understanding of potential paths for humanity. Will we choose to learn from these cosmic events, fostering cooperation and sustainability? Or will we continue to replicate destructive patterns of consumption? The growing interest in cosmic phenomena, including galactic cannibalism, can inspire a shift in public perception. As more people become aware of these events, there is a potential for greater support for scientific research and education. The aspirations for interstellar colonization are another area where galactic dynamics play a role. Understanding how galaxies interact can inform our future endeavors in exploring and possibly colonizing other celestial bodies. Throughout history, the cosmos has been a source of wonder, mystery, and inspiration. The processes of galactic cannibalism illuminate our understanding of the universe and challenge our perceptions of existence. By examining the implications of these cosmic events, we can gain valuable insights into our own civilization, prompting us to reflect on our behavior, values, and responsibilities as stewards of our planet. White holes, theoretical cosmic objects that could appear and disrupt nearby space. The concept of white holes offers fascinating insights into the fabric of our universe, challenging existing astrophysical theories and provoking profound questions about the nature of existence. Unlike their black hole counterparts, which consume matter, white holes are theorized to expel energy and matter, creating a dynamic yet puzzling aspect of cosmic phenomena. This exploration delves into the various implications and concerns surrounding white holes, illuminating how they could reshape our understanding of the universe. White holes' status as an astrophysical conundrum is one of its most fascinating features. Their existence, if confirmed, would call into question long-held assumptions about the nature of energy conservation in the cosmos. According to the accepted ideas, energy can only change forms and cannot be produced or destroyed. The matter ejected by a white hole, however, appears to contradict this idea. White holes may force us to rethink the basic rules we thought we understood if they can release energy and matter without a matching source. In light of the complexity of the universe, this contradiction compels astronomers to re-evaluate long-held ideas about conservation. The implications of white holes extend beyond theoretical physics. They could have catastrophic consequences for the cosmos. A white hole expelling matter at high velocities could lead to shock waves capable of affecting nearby celestial bodies. Imagine a scenario where the energy released by a white hole triggers a supernova in a neighboring star, sending shock waves throughout a galaxy. Such events would not only transform the local environment, but could also impact the broader cosmic landscape, influencing star formation rates and galactic evolution. The gravitational anomalies associated with white holes present another area of concern. If these cosmic entities indeed eject matter, they could create significant disturbances in the gravitational fields surrounding them. Such gravitational waves might alter the orbits of nearby stars, leading to unpredictable outcomes for celestial dynamics. Understanding these potential gravitational anomalies is crucial, as they could reshape how we perceive the gravitational interactions that govern our universe. Theoretical discussions about white holes also bring forth the possibility of spatial-time anomalies. If these entities exist, they might challenge our understanding of spacetime itself. The unpredictable nature of a white hole's matter expulsion could create regions of space that behave differently than we expect. Such anomalies could reveal new aspects of the fundamental nature of reality, inviting questions about how our universe is structured and how we perceive time and space. Connecting white holes to dark energy introduces another layer of complexity to our cosmic understanding. Dark energy is a mysterious force driving the accelerated expansion of the universe, and if white holes are indeed related to dark energy, it could revolutionize our understanding of cosmic growth. The interplay between white holes and dark energy might provide insights into the universe's fate, suggesting that these entities play a vital role in shaping cosmic evolution. The existence of white holes necessitates a re-evaluation of stellar life cycles. Traditionally, massive stars are thought to end their lives as black holes. However, if white holes are real, they could represent an alternate ending to a star's life. This possibility challenges our current models of stellar evolution and may lead to new theories about how stars transition from one phase to another, reshaping our understanding of the life cycle of matter in the universe. Hawking radiation offers a fascinating link between white holes and black holes. For some time, physicists have been curious about the radiation that black holes theoretically release as they expand. White holes, on the other hand, may stand for matter gain, implying a dynamic interplay between the two categories of cosmic objects. Possible new lines of inquiry into the basic mechanisms controlling the energy dynamics of the cosmos may emerge from this interaction. White holes could also yield exciting insights into the cosmic microwave background, CMB. The CMB is the remnant radiation from the Big Bang, and if white holes are active, they might leave distinct imprints on this background radiation. Detecting such anomalies could not only provide evidence for white holes, but also deepen our understanding of the conditions that existed in the early universe, offering a more comprehensive view of cosmic history. If these cosmic entities exist, they challenge our conceptions of existence and creation. White holes could represent gateways to new regions of the universe, posing questions about reality's nature and how matter and energy are distributed throughout space. Role of quantum mechanics in relation to white holes introduces further complexity. If white holes exist, their behavior may provide valuable insights into the relationship between quantum mechanics and gravity. Understanding how these cosmic entities operate could lead to new theories about quantum gravity, expanding our grasp of the universe's fundamental workings. White holes provide serious risks that must not be disregarded. The high-energy particles they can release might endanger nearby celestial planets. Exhaust from a white hole, for example, may cause major atmosphere changes on neighboring worlds. In order to determine if cosmic surroundings are safe and whether life exists in the universe, it is crucial to understand these dangers. Baryon asymmetry is another intriguing area of study connected to white holes. This phenomenon refers to the imbalance between matter and antimatter in the universe. Investigating how white holes might interact with antimatter could yield insights into this mystery, leading to new theories about the universe's composition and the processes that govern it. One of the biggest mysteries in the universe, dark matter, may be better understood with the help of white holes. A possible explanation for the universe's missing mass and its gravitational effects might be white holes that are connected to structures of dark matter. This link has the potential to shed light on the ways in which dark matter influences the visible universe through its interactions with visible matter. The possibility of interactions between black holes and white holes adds an exciting dimension to our understanding of cosmic phenomena. If these two entities are capable of influencing one another, it could lead to the emergence of unique astrophysical events. Exploring these interactions may reshape our perceptions of the forces that govern the universe, revealing dynamic relationships that challenge our current models. If they are capable of redistributing materials throughout the universe, they could significantly influence galaxy formation and the distribution of essential elements for life. Understanding this recycling process could yield insights into how the universe nurtures the conditions necessary for life to thrive. Even in debates about the Big Bang, white holes have consequences. They may provide new light on how the cosmos came to be if they do, in fact, indicate the escape of matter and energy from singularities. Researchers are encouraged to examine new ways of looking at the Big Bang and the role that white holes may play in the story of the universe from this point of view. Temporal distortions are another area of concern tied to the existence of white holes. If these entities are real, they may introduce unpredictable time dilation effects in their vicinity. Such distortions could alter our understanding of time's passage in the universe, leading to new questions about how time interacts with cosmic events. As these ideas enter popular culture, they could inspire new myths and narratives reflecting humanity's attempts to comprehend the mysteries of the cosmos. The evolving portrayal of white holes may shape our understanding of the universe and influence how we conceptualize our place within it. The existence of white holes challenges the fundamental tenets of physics, pushing the boundaries of our current understanding. Their study could lead to the development of new theories that reshape our perceptions of gravity, thermodynamics, and the nature of reality itself. Engaging with the mysteries of white holes may ultimately deepen our appreciation. Solar superstorms, intense sun eruptions. A solar superstorm is an extreme and rare geomagnetic storm caused by intense eruptions of solar energy from the sun's corona. Solar superstorms are far more powerful than solar flares and magnetic storms, and they might have devastating effects on Earth. These superstorms, as rare as they are, carry immense energy from the sun's atmosphere and have the ability to alter our technology-driven world. One historic example, the 1859 Carrington event, serves as the closest approximation of what we might expect today, though the technological impacts now could be much greater, affecting everything from communication to infrastructure and even global economies. Solar coronal mass ejections, CMEs, explosive bursts of solar particles and magnetic fields, are the primary mechanisms that cause superstorms. These CMEs carry charged particles and magnetic fields at extremely high speeds, sometimes reaching over 1,000,000 miles per hour. When they reach Earth, they interact with our magnetic field and produce geomagnetic storms. A key feature of CMEs and superstorms is how quickly they travel. While regular solar flares may take several days to impact Earth, a superstorm-driven CME can cover the distance in just 18 hours, leaving little time to react. One of the primary threats of a solar superstorm is the effect on power grids. The interaction between the incoming solar particles and Earth's magnetic field can create strong ground currents, which induce electrical surges through our grid. The transformers used to distribute power are particularly vulnerable, and if they get overloaded, they can shut down or even catch fire. Replacing these transformers is no easy task. They're expensive, custom-built, and take years to manufacture. A single storm could knock out entire regional grids, leaving millions without power for an extended period, which could translate into a cascading blackout affecting vast areas. Communications and satellite systems face serious risks as well. GPS signals rely on satellite networks which operate within Earth's magnetic shield but can still be disrupted by heightened solar radiation. GPS isn't just for directions, it supports navigation in aviation, shipping, and even timing for financial networks. During a superstorm, signals could lose accuracy or vanish completely. The damage isn't only limited to satellite signals. The solar particles in a superstorm can penetrate the electronics in satellites, potentially frying their circuits or causing them to deorbit due to increased atmospheric drag. Solar superstorms provide unique challenges for the aviation industry. The elevated levels of radiation during these events are particularly intense near Earth's poles, where magnetic protection is weaker. Commercial flights, particularly those flying over polar routes, would expose passengers and crew to higher doses of radiation. The airlines might have to reroute flights, causing delays and extra costs. Crew and frequent flyers would also face elevated health risks, particularly with repeated exposure. Another worry associated with solar superstorms is the possibility of internet disruptions. Subsea internet cables connect continents and are vital for our digital communications. When geomagnetic currents hit, they can interfere with these cables, causing signal loss or even permanent damage in severe cases. Some researchers suggest that the effects could be widespread, knocking out internet connectivity across multiple countries. Since modern economies heavily rely on the internet for everything from communication to trade, a disruption of this magnitude could lead to significant economic losses. Serious repercussions may also hit the financial markets. The synchronization of trades and financial transactions worldwide depends on precise timing provided by GPS satellites. If these systems go down, even briefly, global financial markets could spiral into chaos. The extent of disruption would depend on the severity of the superstorm and how quickly backup systems could be activated. A solar superstorm has the potential to cause extensive radio communication outages. Shortwave and high-frequency radio signals bounce off the ionosphere, but solar storms make the ionosphere unstable, leading to signal loss or interference. Military, aviation, and emergency services use these frequencies, so losing this form of communication could compromise national security and hinder coordinated responses to the crisis. Alternative methods, such as satellite-based communication, might still be affected due to interference in the upper atmosphere. Even while auroras are usually only visible in the northern regions, a superstorm might make them more stronger and visible further south. Auroras aren't dangerous in and of themselves, but they do show how powerful the electromagnetic forces are during a superstorm. Rare auroras seen by people living as far south as the equator during major catastrophes show how devastating these occurrences may be. Apart from the direct impact on technology, a solar superstorm could have indirect effects on other areas of life. Food and water supplies rely on electricity to maintain production and distribution networks. If power grids are down for days or even weeks, grocery stores would run out of food, and water treatment facilities could lose the ability to provide safe drinking water. In urban areas, this could lead to health issues and social unrest as people scramble for basic necessities. Astronauts in space, whether on the International Space Station or future lunar missions, are also highly vulnerable to solar superstorms. Earth's atmosphere provides a natural shield against solar radiation, but outside of this protection, astronauts could be exposed to dangerous levels of radiation. Prolonged exposure would increase their risk of cancer and other health complications, so missions would have to be adjusted or delayed to keep them safe. One unusual effect of solar superstorms is the production of radioactive isotopes like carbon-14. When the high-energy particles from a superstorm interact with Earth's atmosphere, they can create these isotopes, which accumulate in the atmosphere and eventually become part of the geological record. Scientists can analyze layers of ice cores and tree rings to identify past superstorm events, giving us insights into how frequently they've occurred over millennia. Current solar forecasting technology can give us some warning about solar flares and CMEs, but the accuracy and advance notice are limited. Improvements in predictive models are necessary to better anticipate these events, but the inherent randomness of solar storms makes them difficult to forecast. Governments and space agencies have invested in monitoring systems, yet a truly reliable method for predicting superstorms remains elusive. One thing we could do is to improve our response capabilities, building resilient infrastructure like transformers that can withstand stronger currents, and developing emergency protocols for extended power outages would help mitigate the impact of future superstorms. These investments are costly but essential, as our current systems are not designed to handle an event of this magnitude. Our interconnected world, reliant on power grids, satellites, and the internet, faces a unique vulnerability to the sun's extreme outbursts. The challenge now is not only to better understand and predict these events, but to prepare and adapt so that when the next superstorm hits, we're ready to face it head-on. Time dilation near black holes, the cost of venturing close to cosmic monsters. As far as astronomers are concerned, time dilation in the vicinity of black holes is among the most intriguing phenomena. As objects approach a black hole, the intense gravitational pull significantly distorts time. This means that time actually slows down as one gets closer to a black hole, compared to an observer who is further away. This effect becomes so extreme near the event horizon, the boundary around a black hole beyond which nothing can escape, that it almost appears as if time has frozen for the object being observed. To an outside viewer, anything nearing the black hole appears to be moving in slow motion, while for the object itself, time feels relatively normal. One of the most striking examples of time dilation near black holes can be seen when comparing time spent close to the event horizon to time elsewhere in the universe. If an astronaut ventured close to a black hole's event horizon and somehow returned to Earth, they would find that while only hours or days had passed for them, decades or even centuries might have passed for everyone else. This is because time dilation increases as one moves closer to a black hole, making time seem to slow down at an exponential rate relative to distance. The reason time behaves this way is tied to Einstein's theory of general relativity, which posits that mass warps space and time. In areas of strong gravity like those around black holes, this warping is so intense that time itself is stretched out, slowing down dramatically as you get closer to the black hole. This phenomenon doesn't only apply to black holes. We see tiny effects of time dilation around other massive objects, even our own planet, where time moves infinitesimally slower on Earth's surface than it does for satellites orbiting above. Light, too, experiences time dilation as it struggles to escape the gravity of a black hole. When light is emitted close to a black hole, it shifts towards the red end of the spectrum in a process called gravitational redshift. This redshift occurs because the light waves are stretched out by gravity, causing them to lose energy and shift to longer, redder wavelengths. Observers far away from the black hole would see this light as slowed down or lower in frequency, much like how time itself appears to slow near the event horizon. As light approaches the photon sphere, a region around the black hole where light can orbit due to intense gravity, it becomes trapped in orbit, circling the black hole until it either falls in or escapes. The photon sphere offers a unique view of the black hole, as photons emitted from it create a halo around the black hole, revealing its intense gravitational pull and the extreme effects of time dilation in its vicinity. Also subject to temporal dilation is the accretion disk, the whirling collection of matter around a black hole. Here, particles and matter spiral inward at near light speeds, pulled by the black hole's intense gravity. The faster they move, the more time dilates for them, creating a chaotic mix of time frames within the disk. For someone observing from outside, the innermost parts of the accretion disk appear to be moving slower compared to its outer edges. This means that different sections of the disk experience different rates of time. Adding to the complexity of time dilation's consequences are tidal forces in the vicinity of a black hole. These forces pull on objects with unequal strength, stretching them as they approach the black hole. For example, if a spaceship were approaching a black hole, the tidal forces on the side closest to the black hole would be stronger than on the far side, leading to a phenomenon known as spaghettification, where the object is stretched out. Time dilation near the black hole is so extreme that this stretching would occur almost in slow motion from an external perspective, with each moment stretched out as time slows. Larger black holes, especially supermassive ones found in the centers of galaxies, have slightly different time dilation effects compared to smaller black holes. Their immense size creates less extreme tidal forces at the event horizon, allowing for the hypothetical possibility of surviving a journey closer to the black hole without being pulled apart. Here, time dilation still occurs, but in a way that stretches time more gradually, allowing for deeper approaches before the effects become life-threatening. However, in smaller black holes, the tidal forces are much stronger, and the transition into extreme time dilation happens more abruptly. Black holes are known for creating gravitational waves when they collide, sending ripples through space-time. These waves can also carry time dilation effects across space, subtly altering time's flow in distant regions. When two black holes merge, the resulting gravitational waves briefly distort time for regions far from the black holes, showing that time dilation is not just a phenomenon experienced near black holes, but can be felt across vast distances through these space-time disturbances. Another fascinating concept related to time dilation near black holes is the theoretical idea of white holes. White holes are the opposite of black holes and theoretically repel rather than pull in matter. Though they remain hypothetical, white holes are thought to emit particles and light rather than absorb them, potentially reversing time dilation effects and pushing objects and time away from them. This would create an opposite time dilation effect, where time would speed up near a white hole rather than slow down. As scientists study black holes, they use tools like gravitational redshift and the behavior of particles in accretion disks to understand time dilation better. Telescopes like the Event Horizon Telescope capture high-resolution images of black holes, giving indirect evidence of time dilation effects in action. These images show the shadow of the black hole against the bright, warped light from surrounding stars, illustrating the extreme gravitational effects at play. Beyond our observations, the time dilation around black holes also impacts hypothetical interstellar travel. The concept of using black holes to explore the universe, where astronauts could return to their original time period or face extreme age differences, remains largely theoretical. However, it raises fascinating questions about how humanity could explore black holes without falling victim to their extreme gravitational forces. In science fiction, black holes and time dilation have inspired stories and movies that explore time's limits. Films like Interstellar depict characters experiencing time dilation near a black hole, showing the cost of venturing so close to these cosmic monsters. These portrayals bring attention to the real scientific ideas that govern black hole physics and time dilation, capturing the imagination of audiences while grounding the concepts in real physics. Time dilation near black holes demonstrates how little we still know about the universe's most powerful forces. The combination of gravitational waves, event horizons, tidal forces, and photon spheres illustrates the complexity of space-time around black holes. Scientists continue to explore these areas using black holes as natural laboratories to test the boundaries of general relativity and our understanding of time. The influence of black holes reaches far beyond their immediate surroundings. Binary black hole systems, where two black holes orbit each other, create a unique dance of gravitational pull and time dilation. In such systems, the gravitational forces of each black hole amplify time dilation, causing space-time to behave in unpredictable ways. This interlocking pull distorts time and space around each black hole, creating a gravitational field that fluctuates constantly and influences the time frames within its reach. These extreme gravitational pulls challenge our understanding of time and space. Scientists theorize that under certain conditions, time dilation near black holes could lead to scenarios where time itself might reverse. While this remains unproven, it showcases the boundaries of human understanding and the mysterious nature of black holes. The course of stars and galaxies in the vicinity of black holes are similarly impacted by time dilation. Observations show that stars orbiting close to supermassive black holes, such as the one in our Milky Way's center, experience subtle yet measurable time dilation. These stars' motions help researchers understand black holes' influence on space-time and the long-lasting impact of time dilation on nearby celestial bodies. Time dilation near black holes is more than just a theoretical concept. It's a real phenomenon that impacts the universe's most extreme environments. What happens near a black hole challenges everything we know about reality. Moments that last forever, light that fights to escape, and even the possibility of time reversing or freezing. Each discovery brings us closer to understanding the universe's most profound secrets, and pushes the boundaries of science and human curiosity into realms once thought unreachable. In a way, exploring these mysteries is not just about black holes, but about confronting the limits of our own knowledge and asking, how much more is there left to discover? Magnetars, hypermagnetic stars with planet-altering potential. Magnetars are one of the universe's most extreme and enigmatic celestial objects. These are a special kind of neutron star, created when a massive star collapses and leaves behind an incredibly dense remnant. Unlike ordinary neutron stars, magnetars possess magnetic fields 1 trillion times stronger than Earth's, making them not only rare but also uniquely powerful. The magnetic strength of a magnetar defies ordinary physics and makes these stars both fascinating and concerning. While they are far from Earth, a magnetar's capabilities mean that, in theory, even a distant one could affect our planet. The magnetic field around a magnetar can impact its surroundings in profound ways. Not only is it incredibly intense, but it also exerts pressure on the star's crust, creating stress that can lead to a phenomenon called starquakes. These are similar to earthquakes, but on a cosmic scale. When the crust of a magnetar cracks under its magnetic pressure, it releases an enormous burst of energy, often in the form of gamma rays and X-rays. For Earthbound scientists, these bursts are a treasure trove of information. Observing them can help us understand the behavior of matter under extreme conditions. However, they also reveal the destructive potential of these objects, which could cause havoc if a magnetar were ever close to our solar system. In 2004, scientists observed a burst from a magnetar located 50,000 light-years away. The event, caused by a starquake on the magnetar known as SGR 1806-20, was so intense that it briefly impacted Earth's ionosphere. For those few seconds, the burst was as powerful as all the light from every other star in the Milky Way. This particular burst didn't cause any harm, but it offered a glimpse into what might happen if a magnetar were much closer. In theory, a magnetar within 50 light-years could severely impact Earth's magnetic field, potentially even stripping away part of our atmosphere and disrupting global communications. Magnetars are also known for their strange rotational patterns. While most neutron stars like pulsars spin rapidly, often hundreds of times per second, magnetars rotate much more slowly. Some rotate only once every few seconds, and they continue to slow down over time due to a process called magnetic braking. This slowdown happens because the intense magnetic fields of magnetars create a braking effect, draining energy and reducing the star's rotation speed. This unique characteristic separates them from other neutron stars and highlights just how distinct magnetars are in terms of behavior. Unlike pulsars, which emit regular, predictable pulses of radio waves, magnetars are more erratic. They are often radio quiet, meaning they don't emit consistent signals, but when they do, the bursts are powerful and sudden. This inconsistency has puzzled astronomers, as it makes magnetars harder to detect and study. The bursts they emit, while infrequent, are incredibly powerful, often outshining entire galaxies for brief moments. These emissions are primarily in the form of X-rays and gamma rays, making them visible across vast distances and helping scientists map interstellar gas and dust affected by the magnetar's radiation. The extreme density of a magnetar also makes it intriguing. Imagine a teaspoon of a magnetar's material. It would weigh as much as Mount Everest due to its compressed, neutron-rich nature. Inside a magnetar, matter may exist in a superfluid state, allowing particles to move without friction. This state is unlike anything found on Earth and provides a unique environment to study quantum mechanics. Some scientists even suggest that matter inside a magnetar might break down into quarks and gluons, particles usually confined within protons and neutrons. In this way, magnetars open up new avenues for understanding matter at the smallest scales. Magnetars have an effect beyond their local vicinity due to their very strong magnetic fields. It can affect other stars and planets nearby, altering their magnetic fields and impacting their atmospheres. For any planet unfortunate enough to orbit too close to a magnetar, the consequences would be severe. The planet's atmosphere could be stripped away, its magnetic field disrupted, and life on its surface rendered impossible due to radiation levels. Although no planets have been found orbiting a magnetar, the potential consequences for such worlds underscore the dangers posed by these hypermagnetic stars. Given the rarity of magnetars, their impact on the galaxy is limited, but their influence is disproportionately large compared to their small numbers. Out of the billions of stars in the Milky Way, only about 30 confirmed magnetars have been identified. Their scarcity makes each observation valuable, offering insights that more common stars cannot provide. The enormous energy stored in a magnetar's magnetic field could, in theory, power civilizations or fuel scientific breakthroughs if harnessed. However, the risks involved in such close proximity make this more a subject of science fiction than practical science. Magnetars have been proposed as a possible explanation for the enigmatic fast radio bursts, FRBs, seen in faraway galaxies. These FRBs are powerful flashes of radio waves lasting only milliseconds, and their source remains largely unknown. One theory suggests that these bursts could be caused by magnetars experiencing starquakes or interacting with nearby objects in space. If true, this connection could help explain the origins of FRBs and provide a clearer picture of what happens in the environments around magnetars. It's an area of ongoing research, and each discovery about FRBs brings us a step closer to understanding these enigmatic signals. Another kind of high-energy emission that could be associated with magnetars are brief gamma-ray bursts. These bursts are often detected far outside our galaxy and are thought to be caused by cataclysmic events like the collision of neutron stars. Some researchers suggest that magnetar interactions or collisions could contribute to these gamma-ray bursts, adding another layer of complexity to our understanding of the cosmos. By studying these high-energy events, astronomers can learn more about the forces at work in extreme environments and the role magnetars might play in shaping galactic structures. A magnetar may take on a more oblate form than a regular neutron star due to the tremendous magnetic pressure around it. This distortion results from the incredible forces at work within the magnetar, compressing its core and stretching its outer layers. This unique shape gives magnetars another distinction from their neutron star relatives and hints at the powerful dynamics occurring within their cores. The constant battle between gravity, magnetic fields, and rotational forces creates an environment unlike any other in the universe. Despite their power, magnetars are relatively short-lived compared to other stars. Their intense magnetic fields decay over time, causing them to lose energy and gradually fade away. Within about 10,000 years, a magnetar's magnetic field weakens significantly, leaving it to cool and transform into a quieter neutron star. This brief but intense life cycle makes magnetars a fleeting phenomenon, with only a few inactive phases at any given time. For astronomers, this limited lifespan means that each observed magnetar is a rare window into the life of these extreme stars. There's even a possibility that magnetars could interact with dark matter, the mysterious substance that makes up most of the universe's mass. Some scientists hypothesize that dark matter particles could accumulate in the dense cores of magnetars, creating unique effects that might help us detect dark matter. While this idea remains speculative, it highlights the potential of magnetars as cosmic laboratories for studying some of the universe's most elusive properties. If these interactions could be observed, they would provide invaluable insights into the nature of dark matter and its role in the universe. In the end, magnetars represent both a scientific mystery and a potential danger. Their powerful magnetic fields and unpredictable behavior challenge our understanding of physics, while their extreme nature makes them a cosmic force to be reckoned with. Although they are distant and rare, the effects of magnetars can reach across vast distances, impacting everything from neighboring stars to the atmosphere of Earth itself. By studying magnetars, scientists hope to unlock secrets about the universe's most extreme environments, gaining insights that could reshape our understanding of space, time, and matter. Asteroid impacts, the persistent threat of planet-altering collisions. Asteroid impacts capture both fascination and fear. These massive space rocks hurtling through our solar system represent forces beyond our control and carry the potential to alter life on Earth as they have done throughout history. From minor atmospheric intrusions to world-changing collisions, asteroids range in size, speed, and material, bringing both small-scale wonders and serious threats to our planet. Even tiny fragments entering Earth's atmosphere at high speeds can create impressive displays or cause localized damage. The most concerning aspect of asteroids, however, lies in their unpredictability and the sheer power of larger impacts. One of the most intriguing elements is that these celestial objects vary so much. Some are rocky, others metallic, and some even have icy surfaces showing their diverse origins. Many come from the asteroid belt between Mars and Jupiter, while some have been flung in from the outer reaches of the solar system, where they behave as silent relics of planetary formation. This diversity also means that asteroids have different impact effects. For instance, metallic asteroids are denser and can penetrate Earth's atmosphere more effectively than stony or icy ones, potentially causing more powerful impacts. The difference in composition is crucial, not just for understanding where they come from, but in planning potential defenses. A defining feature of asteroid impacts is their infrequency at catastrophic levels. Small-scale impacts are common. Earth constantly experiences tiny meteors, most of which burn up harmlessly in the atmosphere. However, impacts by larger asteroids are rare and devastating. For instance, the Chicxulub impact, which played a significant role in the extinction of the dinosaurs, is a reminder that large impacts have happened and will happen again. The global effects of that impact, including a massive release of energy and the ejection of particles into the atmosphere, created long-lasting cooling and reduced sunlight, a phenomenon sometimes referred to as an impact winter. Such events highlight how the fallout of a single impact can extend beyond the immediate strike zone, affecting climates and ecosystems globally. The idea of an impact winter is among the most worrisome scenarios. Dust and debris thrown into the atmosphere can block sunlight, leading to a cooling effect that disrupts plant growth and food chains. Unlike volcanic eruptions, which can also cool the Earth temporarily, the material ejected by an asteroid impact is often thrown higher and spreads wider, lingering in the atmosphere for longer periods. This effect has severe implications for agriculture, water supplies, and global ecosystems, adding a layer of complexity to the impact of an asteroid that goes beyond the initial energy release. In some cases, the aftermath might be as dangerous as the initial impact, if not more. The Chelyabinsk meteor event in 2013 is a recent example that highlighted the potential for localized destruction. This relatively small object, about 20 meters across, exploded in the atmosphere over Russia with the energy of about 500 kilotons of TNT, damaging buildings and injuring over 1,000 people, primarily from shattered glass. This event showed that even smaller asteroids can have a significant impact if they explode near populated areas. It underscored the value of early detection systems for these smaller objects, which are harder to track but can still pose risks, especially in areas with high populations or critical infrastructure. Asteroids also pose unique concerns based on their orbits and gravitational influences. Near-Earth objects, NEOs, which are asteroids that have orbits bringing them close to Earth, are especially monitored due to their higher likelihood of crossing paths with our planet. But the orbit of an asteroid can shift due to various forces, like gravitational interactions with other celestial bodies, or even subtle effects like the Yarkovsky effect. The Yarkovsky effect, a slight push that results from the uneven heating and cooling of an asteroid's surface, can gradually change its orbit over time. Although this force is minuscule, over millions of years, it can alter an asteroid's path enough to bring it closer to Earth. Moreover, kinetic impact deflection, a strategy for altering an asteroid's course, is an intriguing option. This involves sending a spacecraft to collide with the asteroid at high speed, slightly altering its course away from Earth. Missions like NASA's DART, Double Asteroid Redirection Test, are testing this concept on smaller, less dangerous objects to understand if it could be effective in deflecting a hazardous asteroid. The idea is that by impacting the asteroid early enough, a small nudge can cause a substantial course correction over time, moving it off a collision path with Earth. While promising, this technology is still in its early stages and would likely require years of advance notice to be effective on a dangerous NEO. Asteroids often travel in families or clusters, sometimes even with their own moons orbiting them. These asteroid systems can behave unpredictably because of the gravitational interactions between the primary asteroid and its satellite OAS, adding complexity to any deflection or tracking attempts. Understanding these multi-body systems is crucial, as changes in the orbit of one object within the system can affect the others, leading to unexpected alterations in their collective trajectory. Some of the monitoring efforts for asteroid threats are part of global initiatives like the Planetary Defense Coordination Office, PDCO, at NASA, which works in collaboration with international space agencies to track potentially dangerous objects. They use a variety of telescopes and radar systems to monitor and predict the orbits of thousands of NEOs. This coordination is key to providing early warnings and planning potential missions to avert disaster. Their efforts are complemented by international networks that share data, helping to build a comprehensive understanding of asteroid threats and pooling resources to act quickly if an impact threat is detected. There has been some interest in mining asteroids for their precious metals and iron deposits. Some companies and agencies are exploring the idea of extracting metals and other resources from asteroids which could one day provide materials without impacting Earth's environment. While asteroid mining is still in its conceptual stages, it raises the idea that asteroids could serve both as a source of resources and as objects of scientific study, helping us understand the early solar system's formation and evolution. The potential of a planet-killer impact, although rare, is one reason why asteroid impacts are often compared to other global catastrophes, like supervolcanoes or major climate events. A large enough asteroid impact could theoretically disrupt life as we know it, making planning for these scenarios essential. While it's unlikely that such an impact will occur in the near future, the unpredictability of asteroid orbits and the vast number of undiscovered NEOs leave room for concern. Preparedness and technological development in tracking and potentially deflecting asteroids are key measures that scientists are continuing to refine. Asteroid impacts are particularly dangerous because they are invisible to the naked eye. Unlike natural disasters like volcanic eruptions, people usually have no idea when an impact is coming. Small asteroids can go undetected until they're close to Earth, making timely detection and response a significant challenge. While larger asteroids are easier to track due to their brightness and size, smaller but still dangerous objects require advanced radar and telescope networks to detect, especially those approaching from the direction of the Sun, where visibility is limited. There is an added danger from asteroids that hit water instead of land. An impact in an ocean could trigger massive tsunamis, which, unlike land impacts, would threaten coastlines far from the impact site. These tsunamis could carry debris and contamination into ecosystems, potentially affecting human health, wildlife, and even infrastructure on a wide scale. Coastal cities and islands are particularly vulnerable, as they would experience both the immediate impact and the secondary effects of water contamination, destruction of resources, and habitat loss. The possibility of an asteroid impact is also associated with economic worries. A major collision with Earth, even in a remote area, could disrupt global supply chains, affect trade, and lead to resource shortages. The economic fallout of such an event would extend beyond the impact zone, potentially leading to global economic instability. Cities or regions impacted by an asteroid would face rebuilding challenges, healthcare pressures, and economic recovery obstacles, as resources would be diverted to deal with the immediate aftermath. To fully understand the impact threat, scientists are examining craters left from past asteroid collisions, such as the Barringer crater in Arizona, which shows how explosive even relatively small impacts can be. These craters give insight into the types of forces involved, the extent of the damage, and the lingering effects on the surrounding environment. Research into these craters aids in the development of better models for the prediction and mitigation of future asteroid impacts by providing crucial data on the energy released during impacts. Asteroid impacts have shaped Earth's history in profound ways, contributing to mass extinctions and the evolution of life. The hope is that as we continue to study them, we can improve our chances of mitigating the risks these objects pose, ensuring that we can enjoy the awe of these space visitors without fearing their potential devastation. Grava stars, hypothetical black hole, alternatives with enigmatic properties. A Grava star, or gravitational vacuum star, is a hypothetical cosmic object that is both alluring and mystifying, often considered a black hole alternative. Unlike the typical black hole, which possesses an event horizon and an infinitely dense singularity at its core, a Grava star doesn't collapse all the way down to a singularity. Instead, it's theorized to contain an exotic dark energy core with an outer shell made up of normal matter, resulting in an unusual balance between the intense gravity pulling inward and a repulsive force pushing outward. This unusual structure places Grava stars in a unique category that challenges long-held views on how massive stars evolve, collapse, and affect the space around them. The concept of Grava stars emerged from efforts to address certain puzzles surrounding black holes. Traditional black holes, with their immense gravity and a point of infinite density, create paradoxes that have long frustrated scientists, especially in the context of quantum mechanics. The idea of a singularity, the center of a black hole where density becomes infinite and known physical laws no longer apply, poses fundamental questions about the very fabric of spacetime. Some researchers argue that Grava stars could sidestep these paradoxes, offering a more quantum-friendly cosmic object. By avoiding a singularity altogether, Grava stars could represent a version of collapsed stars that aligns more smoothly with both quantum theory and general relativity. One of the most interesting aspects of Grava stars is their structural composition. Unlike a black hole's event horizon, Grava stars are theorized to have a hard shell of matter surrounding a core of dark energy. This core, instead of pulling everything into an infinite point, generates a repulsive pressure that opposes the gravitational collapse. Essentially, the core's outward push holds back the gravitational force attempting to condense the object further, resulting in a stable state that resembles neither a black hole nor a conventional star. For astrophysicists, this construction presents an intriguing balance of forces that appears both possible and difficult to prove. Another key distinction is that Grava stars may lack the familiar point of no return found in black holes. For black holes, this boundary, the event horizon, marks the limit beyond which not even light can escape. Grava stars, in contrast, might allow certain particles or light to escape or pass through, meaning they wouldn't be completely black like black holes. This feature could theoretically enable astronomers to observe more information about their surroundings or even possibly see into the structure of the Grava star itself. Because of this, Grava stars blur the line between fully trapping light like a black hole and behaving somewhat like neutron stars. This balance between visibility and opacity makes them an enigma, a cosmic object that challenges assumptions about what happens when matter collapses. Grava stars are also tied to the ongoing mystery of dark energy, the force believed to drive the accelerating expansion of the universe. Since their inner core is thought to consist of this repulsive dark energy, studying gravastars, if they exist, could potentially unlock insights into the nature of this elusive force. For cosmologists, this link between gravastars and dark energy adds another layer of intrigue. Could gravastars be small-scale analogs for the cosmic expansion driven by dark energy on a larger scale? Or might they hold clues about the origins and properties of dark energy itself? These questions remain unanswered, but the connections between gravastars and dark energy present a unique avenue for exploring how the universe's most powerful forces interact and shape the cosmos. Observing gravastars directly is, however, a difficult task. Their external gravitational field would be almost identical to that of a black hole, making them difficult to distinguish through traditional astronomical methods. When observing gravitational waves, ripples in space-time caused by violent cosmic events, scientists speculate that the waves emitted by colliding gravastars might differ slightly from those of black holes. This possibility has motivated researchers to examine data from gravitational wave observatories, such as LIGO and Virgo, in hopes of finding subtle clues. If detected, these distinctions could reveal whether some objects previously classified as black holes are actually gravastars, thus reshaping our understanding of collapsed stars. The fact that gravastars don't have any of the paradoxes that black hole theory does, such as the famous information paradox, is another big selling point. When anything falls into a black hole, the information about its initial state is thought to be lost forever, conflicting with quantum theory's principle that information must be conserved. Gravastars, with their lack of a true event horizon and singularity, might preserve information instead of erasing it. If true, this would allow them to sidestep the need for a firewall, a hypothetical zone of intense radiation theorized to form at the edge of a black hole's event horizon. Gravastars may offer a more seamless integration of quantum mechanics into our understanding of the universe by avoiding these challenging paradoxes. Unlike black holes, gravastars would theoretically be stable objects, unaffected by Hawking radiation. Black holes are believed to emit this radiation slowly over time, eventually evaporating as they lose mass. Gravastars, by contrast, wouldn't emit such radiation and could remain indefinitely, suggesting they might be permanent fixtures of the cosmos. This stability, combined with the absence of a singularity, makes gravastars more enduring or even permanent than black holes. For scientists, this has significant implications for theories about the life cycles of massive stars and the types of remnants they leave behind. Despite their hypothetical nature, gravastars challenge the notion of black holes as the universe's most extreme objects. Their existence would imply a wider variety of end states for massive stars, suggesting that black holes and neutron stars aren't the only outcomes of stellar collapse. If gravastars are real, they could belong to a broader spectrum of ultra-dense objects, adding complexity to our understanding of stellar evolution. In this sense, gravastars might offer a middle ground between neutron stars, which are dense but don't collapse into singularities, and black holes, which represent the ultimate collapse. The existence of a gravastar, which combines features of quantum physics with those of general relativity without falling into contradiction, might also provide a solution to long-standing problems in both fields. Physicists have long grappled with reconciling these two realms, particularly when it comes to understanding the behavior of matter under extreme gravitational forces. The gravastar model introduces a cosmic entity that may act as a bridge between these two areas of physics, offering a concept that doesn't violate established principles yet still exists in the extreme conditions of stellar collapse. This hybrid nature of gravastars could pave the way for theories that unite general relativity and quantum mechanics, two pillars of modern physics that currently don't align. Gravastars are as mysterious as they are revolutionary. They invite us to consider alternatives to the gravitational extremes posed by black holes and the singularities that strain the fabric of spacetime. Rather than fully collapsing, gravastars propose a new cosmic endpoint, one that preserves the structure of a star in a way that could reveal deeper truths about the universe's fundamental forces. Even if gravastars remain hypothetical, Their conception alone pushes the boundaries of astrophysics and theoretical physics. By presenting an alternative to black holes, Grava stars encourage scientists to look beyond traditional models of collapsed stars, fostering new perspectives on how the universe might work at its most extreme. The universe, filled with mysteries like ghost galaxies made almost entirely of dark matter and cold star clusters hiding in desolate voids, shows us how vast and unpredictable the cosmos can be. Concepts like false vacuum decay, a theoretical event that could reshape reality as we know it, or zombie stars, white dwarfs that reawaken by consuming neighboring stars, remind us that space isn't just a passive backdrop, it's an active, shifting landscape with phenomena that challenge our understanding of physics and life itself. Even our own solar system has its strange limits, like the hydrogen wall, the sun's protective edge against interstellar forces, adding layers of complexity and fascination. Each of these unique facts transforms the stars from distant dots to dynamic forces, forever changing the way we look at the night sky. I hope you enjoyed the video. If you did, feel free to subscribe. Thanks for watching.